We're going to open up with Thomas Brazelton. Go ahead.
Cool. Awesome. Thank you to the organizers for having me. Thanks everyone for being here this morning. And welcome back to FrankFest Day 3, or I guess the Computational and Applied Enumerative Geometry Workshop, what we've been calling it. I've got the unenviable task of being the first talk after the unofficial, very unsanctioned roast of Frank, so I'm hoping to bring us back to math a little bit, but hopefully not excite you so much that you can't enjoy a Wednesday afternoon. So if you find yourself kind of like, man, at the end of the talk, it was intentional. Okay, so I'm going to tell you about a Macaulay2 package that I wrote with Nikita Borisov, Franley Espino, Tom Hagedorn, Jabo Han, Jordy, Joel Ausma, Gabe Ong, who was mentioned in Julia's talk, and Andrew Tawfiq. And I'm going to try to tell you a little bit about how to do A1 Brouwer degree computations with an eye towards A1 enumerative geometry, which uses the machinery of A1 homotopy theory at a conference for a lot of applied algebraists. So it's a lot of stuff that's going to happen, and I'm going to try to say what I can about why you should care about these computations, but I might ask you to suspend a little bit of your interest until Friday, when I'll be able to say more about A1 Brouwer degrees in the context of enumerative geometry, and hopefully Kirsten in her talk will be able to talk a little bit more about A1 enumerative geometry and the types of questions you can solve there. Okay, so I want to start with classical Brouwer degrees, which if I have a polynomial map from C to the n and C to the n, and 0 is some regular value, then I can look in the pre-images of 0, and I can compute what's called the local degree at each of these things. And this is a very granular invariant that we sourced from differential topology. This tells you basically an integer value of how many points are in the fiber of a regular value counted with some sort of multiplicity. And this local degree, there's a lot of ways to compute it, but roughly speaking, it has a homotopical definition. I can take this thing and I can extend it away from polynomial maps to smooth maps, and often to continuous maps. And it's not important that it's C to the n here, right? I could look on charts and do these sorts of things between smooth, compact-oriented manifolds of the same dimension. And I get this really broad thing that allows us to do a lot of really cool things across all of topology. And what we might know this as is something slightly different, which is intersection multiplicity of the component functions of f. What this is picking up for you at a local point P is how the hyperplanes corresponding to f1 through fn are intersecting with some multiplicity. And now if I do this sort of thing over the reals and I look at the Brouwer degree, it's no longer true that I'm covering the size of the fiber counted with multiplicity. This is sort of the difference between the reals and the complex numbers when I'm doing these sort of computations in differential topology. And to tell you what I mean by this, I want to look at this graph where I'm taking the reals and I'm mapping to the reals by sort of taking the red line, folding it up, and then projecting it down here. And what I see is that the local degree at each of these points in the fiber is computing something for me. It's first of all computing multiplicity, and these all have multiplicity 1, which is great. But it's also telling me how an orientation around the point is either being preserved or being flipped. So if everything's oriented left to right, at this point right here, the orientation is being preserved. At that middle point, it's being flipped, right? I have some orientation on R, and that's being turned around in the local neighborhood of that point under the map. And then up top, it's being preserved as well. So if I ran a Brouwer degree computation of this whole map, I would sum over the points I see in the fiber, and I would see a +1. So what this is picking up for me, again, is not the size of the fiber. It's a weighted sum over the fiber. And what I want to sort of advertise, it is a lower bound for the number of points. Yeah, absolutely. Yeah. OK. So what I want to sort of pose for everyone is this idea of quadratically enriched geometry. And the idea is to take classical integer valued things, so things like intersection multiplicity, and replace these with quadratic forms. And this allows you to get answers over any field that you can again sort of go in and interpret. So what I want to say, first of all, is I'm going to recap quadratic forms, symmetric bilinear forms very briefly for everyone. All the fields are not characteristic to, if that's something that you know about. Then I want to define, or at least sort of talk about what quadratic intersection multiplicity is and how it relates to these pictures we've seen of Brouwer degrees. And then finally, I want to talk about doing some sort of coding and doing quadratic enumerative geometry and answering questions over other fields. OK. So the home for all of our invariants is going to be some place where symmetric bilinear forms sort of naturally live up to isomorphism. And this is called the Grothendieck-Witt ring of a field. And I should think about this as non-degenerate symmetric bilinear forms defined up to isomorphism And then for formal reasons, we group complete with respect to block sum. And this is additively generated by these sort of very simple rank 1 forms on your field. So I take a pair x and y, and I map it to a times x times y. And if a is a scalar, that's going to be non-degenerate. And then one of the things that I wanted to say, right, is like I want this up to isomorphism. So I could change a basis downstairs. My basis was 1 on each of these copies of k. And I could just let it be b for some scalar b. And I would get the form that goes, x, y goes to abx, aby, or abx, by, which is like ab squared. So all of these things are generated up to square classes. And this will end up being sort of tremendously important in the computations that we do. OK, so we can load our package in, which is called A1 Brouwer degrees. And this is going to let us do computations that will be valued in the Grothendieck-Witt ring of certain fields. So what I want to do is if I have a matrix that's defined over something like the rationals, I can take that matrix and I'm going to store it as a Grothendieck-Witt class type. So what this is it has in its cache, it has a representing matrix that's a symmetric bilinear form. But we're allowed to sort of check when two symmetric matrices are giving you the same form over a field. And so this is just like a new type that we've invented. And we have all sorts of manipulations that you can do to do arithmetic inside of the Grothendieck-Witt ring, if that's something you're interested in doing. OK, so here's a famous example of a quadratic form or a symmetric bilinear form. This is called the hyperbolic form. And if you diagonalize it, it's equal to 1 plus minus 1. So it's the same. It's congruent to the matrix that's 1, 0, 0, minus 1. And we can build this sort of thing over a field that we want. So here we have a finite field. And I can build a hyperbolic form. This gives me a class in Grothendieck-Witt. So if I want to sort of mess around with quadratic forms, I can do this. And if I wanted, instead of a 2-dimensional one, let's say I wanted 3 copies of them, I could specify some sort of dimension in a second variable and get something like that. OK.
So if you put an odd number, does that fail?
It'll fail, yeah, if you put an odd number in.
Basically, or
I don't know. You should get the package and find out. So I can also specify a list of integers for you, or a list of elements over your field. And I can produce a diagonal form here. And this is the diagonal form 3, 6, 7. And there's this old theorem that goes back to Sylvester, which says every form is isomorphic to a diagonal one. What this means is that every symmetric matrix will be congruent to one that's diagonal. And again, this is not diagonalization of matrices, right? You're not getting eigenvalues. What I'm doing, roughly speaking, is I do a row operation, and then I immediately do the same operation on columns. And this preserves the symmetric structure. And that's how you would diagonalize something.
so this is independent here.
Yes, yeah. So it's stated over R. It works over any field, not characteristic 2 again, but yeah. OK. So let's say I have some sort of form that I'm looking at. So I've got this Grothendieck-Witt class here. We can run a diagonal class computation, which will diagonalize this form for us and then give us some sort of nest diagonal element. And in a lot of our methods, when you have a diagonal representative, that gets cached so that it speeds up computation later on. OK, so let's see some examples. So over the complex numbers, what I do is I take some symmetric matrix. We apply this theorem. I can diagonalize it. I get entries along the diagonal. And let's remember that each of those entries are the additive generators. And they only matter up to a square. And every unit is a square in C. So every matrix of rank n is isomorphic to the matrix that's just the identity matrix. So forms are completely classified by their rank. And this gives you an isomorphism between the Grothendieck-Witt ring of C and the integers after you group complete. And this holds for any quadratically closed field. Right? Anytime I diagonalize and then look at the square classes, they're all going to be the same as 1.
What do you mean by quadratic closed?
Closed under quadratic field extensions. Yeah. OK. Over the reals, I can run the same game. I'm going to take some form. I'm going to diagonalize it. And then I'm going to get these diagonal entries that are either going to be positive or negative. And these are 2 different square classes. So I can arrange to have just 1s and minus 1s along my diagonal. That's something I'm capable of doing. And then what I could do is I could take the trace of that matrix. I'm just going to sum up the diagonal entries after they're 1 and minus 1. And this is something that's called the signature of your form. And rank and signature together jointly classify symmetric bilinear forms over R. So I need this second invariant. So if I look at this form beta that we had on the other slide, what I could do is I could run this signature here. And what I get is 1. So this tells me this form over the reals is isomorphic to any other rank 3 form that has signature 1. OK, so We talked about having Brouwer degrees. This is some definition in differential topology that's detecting basically how a local neighborhood is changing under a map. And if I have a map of varieties, if I have a map from AN to AN over an arbitrary field, you can define a notion of Brouwer degree, which is due to Morel, and this is valued in the Grothendieck-Witt ring. And it uses a lot of very heavy machinery from motivic homotopy theory. And when it was originally defined, there was sort of no computational way to go about it. There were very small cases where we knew how to compute it. In general, we had no idea. We had no algorithms for these sorts of things. Now, one way to sort of interpret this is you look at this algebra right here, where if this was C, and I zoomed in at this sort of thing, right, this is maybe P is a 0 of this map F. If I zoom in at this and I was over an algebraically closed field, if I took the dimension of this as a k-vector space, it's exactly telling the intersection multiplicity. This is the classical definition of intersection multiplicity. And the idea, what we want to do is replace that by a symmetric bilinear form on this algebra. So the rank, again, would recover the intersection multiplicity if you base change to an algebraically closed field. But there's so many more invariants on symmetric bilinear forms that you could use to study, depending on the sort of complexity of the field that you're looking at. And these bake in really interesting information. Yeah? Yes, yeah. These are the component functions. Or you could think about these are the hypersurfaces, and they're intersecting at P, and we're studying how they intersect quadratically. OK. So if I were over the reals, I could take an A1 Brouwer degree, and I get a form in Grothendieck-Witt of R. And again, we need rank, and we need signature to classify this form. And the rank, again, is telling you if I base change to C, how many points do I see in the fiber. And the signature is telling you something slightly different. So here's an example. So I'm going to take this cubic, which was like the picture we saw earlier, the z minus 1, z plus 1. And I'm going to compute a global A1 degree of this. And I get this matrix. And in many cases, you want like a nicer looking form. So we have this string method that gives you something a little bit more readable. And this tells me, OK, I've got a hyperbolic form plus bracket minus 1 here. And what I want to do is interpret this as a quadratically enriched intersection number. And the minus 1, I think, was a feature of the orientation being flipped. But basically what's happening here is if you think about this polynomial as it crosses the x-axis, if I just counted the roots, I'm counting 3. And that's the rank of that form we just saw. What I want to do instead to get the signature is count with some extra data. So let's orient each of these things. And I'm just going to do like a right-hand rule every time I see a crossing. So I'm going to go up this way, and then I'm going to stick my finger out. I'm going to add, let's say, like a minus 1 here. And then I'm going to come back, and I'll stick my finger in the direction of the x-axis. I get a plus 1. And then I do this, and I get a minus 1 over here. And that's what that signature is telling you. So if I took the signature of the global A1 degree of this, in this case, it's telling you 1. And what that says is, OK, if I do that, I'm getting 1 plus minus 1 plus 1. So it's picking up intersection weighted by a right-hand rule. If you were working over other fields, let's say we were doing something over a finite field, what you're picking up is something a little bit different. You're actually picking up a signed volume of the parallelogram spanned by the tangent vectors at the point of intersection. There's this beautiful work of Stephen McKean that makes all of this precise. But it really is baking sort of interesting geometric information when you zoom in. So this leads to an idea of quadratically enriched enumerative geometry. Right? When I can do things like intersection multiplicity, you might sort of talk about counting things and answering problems. And now we want to answer them over an arbitrary fields and get a symmetric bilinear form as an answer, quote unquote. So this is a program of math that I think Kirsten will talk a lot more about on Friday. This is called A1 enumerative geometry, quadratically enriched enumerative geometry, sometimes just enriched enumerative geometry. And one of the main tools that we use is this A1 Brouwer degree that I've been talking about. And this helps us solve problems. So I want to give you sort of one example of the type of problem you could solve with this, which is a theorem of Jesse Cass and Kirsten Wickelgren, which says the number, I put that in quotes, of lines on a smooth cubic surface over an arbitrary field is this form 15(1 plus 12 minus 1. OK, so what am I seeing? So if I specialize the field to C, I just get 27. That's the rank, and that's the classical computation. If I go over R, I see I need signature to classify this, and then I get 3. And what this is telling me is that when I count over the lines together with some extra geometric data that's being picked up by the A1 Brouwer degree, I'm getting 3. And here's the data that we see. So if I have a line on a cubic surface, do you still have a model of one, Frank?
Yeah. How many do you want?
I'll just grab one. if you have a line on a cubic surface, thanks. The idea is to sort of find your line, and then let's say you drop like a skateboard on a point on the line, and then you skate along the cubic surface, and you go out to infinity, and then you come back, and you either came back on the same side, or you came back flipped. And so let's count the lines that I see with a 1 if I come back on the same side, and a -1 if I come back flipped.
I see, so like this, like a rewarding class.
Basically, yeah. It's do you lift to the frame bundle, the double cover of the frame bundle, yeah. Okay, so this dates back to work of Segre in 1942. He was sort of the first one to notice this. Has been proven and reproven over and over in the literature. But that signature is telling you there's a weighted sum over these things. And I have like 4 possibilities of lines on a cubic surface over the reals. If I summed over each of those together with that data, I'm always getting 3. So this is a constraint. It's a geometric constraint to the types of solutions you could see. Over finite fields, you can similarly define these things. You have to be a little more careful about how you define what we call the topological type of the line. But this is constraining the fields of definition of where the lines are allowed to be defined. Yeah, Jake.
In the finite field case, you get, so here I guess you get the lower bound, but there's at least 3 lines.
Mhm.
You get that over a finite field, there's at least 3 that are rational over a finite.
No, not necessarily.
Typically, yeah, I mean, you're not going to get like that. If you look, I mean, you look at the Galois group, not all the elements have 6 points.
Yeah.
So,
Okay. Yeah.
So were you telling us that there are 15 that do flip or 12 that do flip?
15 that do and 12 that don't, if you have 27 lines. If you had 15 lines, let's say, you would have 9 that don't flip and 6 that do.
Okay.
Yeah.
So there's 15 that don't.
15 that don't, 12 that do. Maybe I said that wrong.
If you
Yeah.
have 27.
Yeah. Okay. So
rather than say flip, I mean, you just look at the germ of the surface along that either it's a Möbius band or it's not.
yeah.
And that's what you're.
Okay, so how might I compute something like this? If I have a section of this bundle, it's the same data as choosing a cubic surface. And when I trivialize a section over here on an affine chart, this section gives me on charts an endomorphism of affine 4 space, right? It gives me a map from, let's say, k to the 4 up to k to the 4. And I can count the global degree of this thing. And I'll see this section vanishes on a 2-plane in 4 space if and only if the projectivization of that is a line that lies on the cubic surface. This is a way to count cubic surfaces, or lines on cubic surfaces using characteristic classes, let's say, if you're over R or C. Okay, so I could fix a basis for K4, and I could take the span of this sort of thing with these yi's. And what this is giving me is a trivialization of an affine cell on the Grassmannian. And I could look at the induced map up to Sim3S dual, and I get this type of section right here. So what I could do is I can compute its A1 degree, and I get this big, gross, nasty matrix. And again, we want to run our string method. And what I'm going to get is 8h plus 1 plus 1. So this is telling me over the affine patch that I parameterized, I'm seeing exactly 18 lines. And they're weighted in this sort of way. I've got 10 of them that don't flip, and I've got 8 of them that do flip.
Why does it say plus 2 times 1?
I don't know. Someone else was in charge of that on the project. That's what I'll say. Okay, so I can actually find a line in this sort of thing, and I can interpret its local A1 degree. So if I look at the minimal primes here, I could pull out one of these lines. And this is the one defined by this equation. And I can compute the local ideal, the local degree of my thing at this thing. And what I get is a matrix. It's a 1-by-1 matrix with 81. And this is a square, so I get plus 1 here. And this is telling me for that specific line, when I go along the tangent bundle, it doesn't come back flipped. It stays the way it was. OK. So in the remaining couple minutes, I want to say a little bit about how you actually compute these things. There's a long history for this. This dates back initially to work of Eisenblatt and Levine in the 70s. And Kim Chiashvili was working on this at the same time. And what they said basically is in differential topology, so not even algebra, just in differential topology, if I have a smooth map between manifolds and I zoom in at a point and I want to compute its local degree, what you normally do and what you would learn in a manifolds course is to take the sign of the determinant of the Jacobian at that point. And what they were asking is just what if the Jacobian vanishes, right? What if there's some higher multiplicity? How might I detect sort of a weighted sum over the signs of these things? And they developed this beautiful commutative algebra formula that works over R, but really should work over any field. And they conjectured this is some form of a degree in some form of homotopy theory over some other fields. I said something sort of to that effect. Around the same time, Shea and Stork were working on doing sort of quadratic forms that talk about intersection multiplicity of complete intersections in this beautiful but really hard to read paper from 1975. And then in the early 2000s, in like 1999, A1 homotopy theory was being developed, and Morel had this notion of degree that he was working on. Lin and Morel talked about how to compute some very early examples of this. Christoph Kazanov in his PhD thesis, which is this amazing work, talked about endomorphisms of the projective line and how to get quadratic forms out of these that tell you some sort of geometric information. And then Jesse Cass and Kirsten Wickelgren had this fantastic paper in 2019 where they said, you remember this form from the 70s that they said should have been a degree in topology. It actually is the degree coming from A1 homotopy theory, and here are some basic ways to compute it. And Tom Bachman and Kirsten Wickelgren have also aligned this stuff with the Shea-Stork work. And then in recent years with my co-authors, we developed sort of some broad techniques for computing these things, some sort of very, I want to say like efficient algorithms, at least efficient compared to what had been done, that allow you to compute these. One of the big advantages of our work over the stuff that came before us is we can compute global A1 degrees without summing over local things. In other words, if I have my maps, I don't have to solve for all the things in the pre-image, which is the most costly part of the computation. If I want to compute a global thing, I can just do it on the global algebra without even understanding what the zeros are. So why might this be advantageous? Let's say I've got some smooth K-variety, and I have a section of the tangent bundle. In topology, if I take the degree of this section, right, if all my zeros lie on some sort of thing, this is giving me the Euler characteristic of the manifold itself. And so let's suppose I can find a section where all the roots are lying on one affine patch. Then I can trivialize over this path, look at the induced map on the section, and just compute the global thing without solving for the zeros of the vector field. And this is a way to compute an Euler characteristic. So I want to give a very quick example of this in my remaining time. So if I have an arbitrary Grassmannian, there actually exists such a section. There exists a vector field along the Grassmannian where all the zeros are lying on one big affine open cell. And we can find such a section. So in the case of GR24, we've written it out, and it's in my paper if you want to see this. But this is what you can do. And you can, this is for, no, this is just a section of the tangent bundle. Yeah. And we can compute its global A1 degree here. And again, right, all the zeros were lying on one patch, which is super important for us. So let's look at this thing. So what am I getting out of this? I get some 6 by 6 matrix. It has rank 6. And 6 is exactly the Euler characteristic of the complex Grassmannian 2-4. And this is not at all a coincidence, right? We're getting some form whose rank should recover the Euler characteristic over C. And then I run the signature of this thing, and I'm going to get 2. And does anyone know what the Euler characteristic of the real Grassmannian 2-4 is? It ends up being 2. Okay, so this is a general method for computing Euler characteristics. And in any setting where you have a variety that you want to study from the perspective of A1 homotopy theory, one of the first granular invariants you might want to extract is a quadratic form valued Euler characteristic. And this is a really nice way to do it that runs very quickly. And I also just want to advertise Euler characteristics of Grassmannians are binomials, which means you should put them in a Pascal's triangle. And this is how you do it quadratically. And this is a really fun picture that's in our paper. And there's this sort of colored rule for adding things where if you have something up to the, if blue is in the top left, you just add them like normal. And if white's in the top left, you add -1 times the thing to the top right. And that's how you do these sorts of things. Okay. So takeaways from this. Here's our package. It's available in Macaulay2 now. We've got documentation on archive that we're hoping will be through the JSAG process soon enough. This allows us to get quadratic intersection multiplicity. It allows us to do it locally, but also to do it globally. And again, the key point for that is to avoid local computations if you want to do it globally. Something I tried to advertise a little bit, we can extract invariants out of quadratic forms, which is what we need to classify them. So we can get rank and signature, discriminant when we're working over finite fields, and then Hasse-Witt invariants, which is what you need to classify over the rationals. And the last key point is that we had this thing that takes a big form and decomposes it into something that you can read. This is decomposing forms into the isotropic and anisotropic parts. From a computational standpoint, this is absolutely the hardest part of the package, is extracting the anisotropic part of a quadratic form. But we have it baked in there and ready to use, and I think that's just about my time, so thanks.
Any questions? Too polite here.
Yeah. So one of the things that this package does is it's working a lot with growth and decvit. And we've seen it now as a group, but the growth and decvit ring structure, is this baked into the package as well? And
Yes, yeah,
Oh, great,
absolutely.
fantastic.
Yeah.
Okay. Yeah, that was my question.
For your listed fields, are there any other fields where there are potentially algorithms for running, like, say you want to do it over QP or over FQ adjoin T or some more complicated field?
In our package right now, this is all that's supported, but that's mostly due to sort of what Macaulay2 can support as far as fields are concerned. The algorithms that are outlined in my work with Stephen and Sabrina work over arbitrary fields. And this is one of the key results in our thing is we were only really able to do perfect fields before this. Now you can do enumerative geometry over imperfect fields if you want to. So if you wanted maybe the function field of a curve or something to study something over that, you could do it.
And so if somebody here wanted to use this package today,
Yeah.
do we have to upgrade our Macaulay2, or is there a place that we can just grab this code and load it in?
If you are, I think now 2 releases behind Macaulay2, you won't be able to get this. But yeah, so this is, I mean, you can go through GitHub to get it. There's a link in our archive paper. It's what?
There's Macaulay2 online.
Oh yes, yeah, you can do it through a browser if you want it as well.
Well, the right answer is you should upgrade your Macaulay too.
I wasn't gonna say it, but yeah, Frank will.
Okay, thanks.
Yeah.
That's a great, it's like flossing. Okay, so have you used this package to compute anything new or surprising?
Me, no. Sabrina Powley is like actively using our package and emailing me constantly about it. She does this stuff that sort of combines tropical geometry and A1 enumerative geometry, and it's found like a lot of uses there.
All right, let's thank the speaker again.